Hello and welcome back to the last week's lecture of this NPTEL course on thermal physics. Now, up to previous week we have been talking about classical thermodynamics, thermodynamic potential, thermodynamic processes, equilibrium, and also we have discussed phase transition, phase rule, all these things. This week we will be discussing something totally different. We will be talking about radiation. Now, what is radiation? What are the implications or what are the connections of radiation with thermodynamics, classical thermodynamics, and and also what are the usefulness of different laws of radiation. We will see that during this segment. Also, towards the end we will dedicate some time towards in the discussion of the third law of thermodynamics. Now, let us start without any further delay. Now, radiation means that is every object above absolute zero temperature. That essentially means every object, because we will see the one of the logical conclusion of third law of thermodynamics is that absolute zero cannot be reached by any finite number of processes. We will see. We will come to that towards the end of this week. That means the end of the course. But when we say above absolute zero, that essentially means practically everything, because nothing can be at absolute zero, emits something called thermal radiation. Now, what is thermal radiation? Thermal radiation is certain amount of energy that get released from the surface of any object, and the underlying the source of this energy is underlying molecular level rotation and vibration. For solids, we can realize that there should be only vibration, there is no rotation, underlying rotation, but for liquid and gas it could be vibration and rotation both. So, the energy is emitted from the surface, but the source of energy is inside the object itself. So, it is there for the entire volume. This emission rate, what we are talking about, the radiation rate, that I would say, it's a function of temperature actually. We will see later on in a more formal manner that as the temperature increases, the rate of radiation also increases. There is a very famous law in the name of Stefan-Boltzmann called the Stefan-Boltzmann law, that says this that actually proves this phenomenon. But even without that, we can understand that if we are standing next to a hot object, we can feel some heat, like if we are standing next to a fire, or if it's a very hot day and we are just outside on a maybe there is a courtyard where it's fully illuminated by direct sunlight. Even if we are not inside into the sunlight, we can actually feel the heat coming and touching our skin. So, that is what. So, that means typically temperature is we can actually feel the radiation by virtue of our senses, right. So, again these are the laws. Like every other branch of physics, radiation is also something that started off as an observational science, right. So, there are certain properties that has been observed later on. So, initially it was only qualitative, later on it became quantitative, and then it was formalized into mathematical laws, right. Right. Now, it was also proved later on that radiation, including thermal radiation, I mean there could be thermal, I mean it could be non-thermal radiation as well. For example, this one, the radioactive radiation, X-ray radiation, these are not exactly thermal radiation by nature. So, we do not get gamma rays out of an object just by hitting it. There has to be some sort of underlying radioactive process in order to get a gamma ray. But all this radiation, let it be gamma ray, let it be X-ray, let it be IR, let it be microwave, these are thermal, I mean including thermal radiation, this is electromagnetic in nature. and radiation in general is a volumetric property. So, that means radiation is emitted from the, although we sense it from the surface only, radiation is there even inside the volume of an object. And we will see later on that we for a closed radiation, closed cavity radiation, we have to define the energy density per unit volume of radiation. Okay. So, let us take some example of radiation. Every object is a possible source of thermal radiation. So, if we just observe the IR, shot, a normal shot, it is a night vision actually. So, street and some cars going, some people are moving, yeah, there is a lamp post here, there are buildings, trees, everything is there. It is a night shot. Why? Because you see the sky is dark. So, there is hardly anything coming from the sky. So, that means it will tell you that it is a night shot, right. Now, what do we have here? This is basically a thermal image, heat map. So, actually it has been captured using a infrared camera. So, even if we do not see things with our naked eye, because in the dark, because what we see, these are actually reflected lights, it is not radiation as such. When you look at me, what you see, or when you look at the screen, okay, that is a different issue altogether, because the screen actually has some radiant properties to it. But if you are talking to another person face to face, when you see that person, what you see exactly is the light reflected from that person's face, person's body. But in dark condition, there is no reflecting rays. So, our eye failed to see anything, but at the same time, as long as everything, every object, as I have mentioned already, it radiates heat energy. Even in the dark, an IR camera can sense the small, the heat radiation coming out of any object, and this is exactly what we see through an IR camera, right. And here actually that can be converted to temperature. So, we see there is a temperature scale in degree centigrades given to the right. The black is 18 degrees and the brightest one is the pink, which is 32 degrees. We see these cars, the car tire which is hot, actually the road above which the car moves is hot. So, that is why in this region we have very high temperature. There must be something up here. So, that is why it is high temperature. Tree is 20 degrees, buildings are 24 degrees, like that. So, these are typical IR thermal imaging captured by IR. Now, this is something that we know exists, and probably all of us have seen shots, pictures taken by IR camera. But for myself, I have never seen an IR camera myself. I do not know how it looks. I just know that it can capture thermal image. But there are certain things that we might have experienced. For example, if you have visited a blacksmith, he is making something, or a foundry sometime in your life, you might have seen this type of red hot metal. This is a piece of steel, red hot steel, which is going inside water for certain processing. Anyway, so immaterial, but what you see is a metal surface which is typically dark in color, or maybe shiny, but definitely not red, becomes red when it is hot. Not only that, a tungsten block can be white. It is even hotter than the red one actually. Okay. So, it becomes white almost. So, this is called white hot condition, and this is a tungsten metal. Photo sources are given, so you can have a look. So, this is a steel, this is a tungsten, and to your right, bottom right, what you see here is actually a blue white radiation from carbon arc. So, this is the arc that has been created inside vacuum between two carbon electrodes, solid carbon electrodes, and we see this radiation is blue white in nature. There is a definite bluish tinge. Now, that tells you that thermal radiation can have a very wide range of spectrum. We can have IR, we can have red, we can have whitish yellow, which is somewhere in the middle of the visible spectrum. We can also have violet, blue or violet, which is towards the high end of the low frequency limit of the visible spectrum. Now, indeed, this graph here actually shows you that thermal radiation is it can span from infrared to all the way into ultraviolet regime. Now, it does not mean that there cannot be thermal radiation in the microwave region, okay, or there cannot be thermal radiation in the deep ultraviolet or higher X-ray region. It is also possible to have such radiation, but typically these are very rare. Now, in this chapter what we are going to do is we are going to treat thermal radiation as a thermodynamic system, but at first we need to learn few definition before we can go there. Okay. And also we will talk about little bit about the spectrum, the possible spectrum of a black body, which covers the entire thermal radiation range. There we will see that thermal radiation can have the frequencies can be in this very small wavelength or short wavelength and very long wavelength region as well. Anyway, so let us move on. The first definition that we are going to learn is the spectral energy density. So, that eventually is called U lambda, and U lambda d lambda denotes the energy per unit volume, once again because radiation is a volumetric property, per unit volume in the wavelength range lambda to lambda plus d lambda. So, U lambda should be energy per unit volume per unit wavelength at lambda at the wavelength lambda with an units of joules per meter to the power minus 4. Why? Because if U lambda has units of joules per meter to the power minus 4, then U lambda d lambda will be in the units of joules per meter cubed, that means energy per unit volume, right. Similarly, the total energy density, which is total radiant energy at any point over all possible wavelengths per unit volume around that particular point. So, we may write, we can correlate this two, and we can write U is equal to integration 0 to infinity U lambda d lambda, where the integration is over all possible values of the wavelength. Now, obviously, the unit of U will be joules per meter cubed, because you see U lambda has an units of joules per meter to the power 4. We are multiplying this with lambda once again. So, the units will be joules per meter cube, right. Spectral emissive power E lambda of a body for the wavelength range of lambda to lambda plus d lambda is defined as the radiant energy per second per unit area in the said wavelength range. So, if the wavelength range in question is lambda to lambda plus d lambda, E lambda is the amount of energy that is been radiated in this wavelength range per second per unit surface area, right. Similarly, emissivity, which is an integrated form of E lambda, it gives you the total amount of radiation for all possible wavelengths, and once again here the wavelength range, all possible wavelength of an object per unit area per unit time. So, this will be E is equal to integration 0 to infinity E lambda d lambda, where unit of E is joules per meter square per second. So, meter square because joules for energy, meter square because it is per unit surface area, and second means it is per unit time. So, we can write joules per second as watt. So, we can simply write this as watts per meter square. Remember, understand this, that in both cases the integration limits are 0 to infinity here and here. So, that also tells us that although typically the thermal radiation falls inside this range, we can in principle have thermal radiation in this and this ranges as well. So, this is your wavelength range of 0 and this is your wavelength towards 0 and this is your wavelength towards infinity. Okay. Next is spectral absorptivity A lambda, which is defined as the fraction of incident energy that is being absorbed per unit surface area per unit time between wavelength lambda to lambda plus d lambda. If d of q lambda is the total incident radiation in the wavelength range lambda to lambda plus d lambda from all direction, then A lambda delta q lambda is the energy absorbed per unit area per unit time. Okay. So, this definition is something that we are going to discuss once again when we will be proving Kirchhoff's law. Okay. And A lambda is a dimensionless constant, it is a dimensionless number, and we may define R lambda and T lambda for the as the spectral reflectivity and spectral transmissivity respectively. Then for any radiation that is falling on any object, part of it will be reflected, part of it will be absorbed, part of it will be reflected, and rest has to be transmitted. That eventually means A lambda plus R lambda plus T lambda has to be equal to 1, because if total energy delta q is absorbed by a surface falls on a surface, the total amount that will be reflected plus transmitted plus absorbed by the surface should be equal to delta q lambda. Right. Once again, these quantities they change with wavelength. So, we are not mentioning it explicitly, but as soon as we have this lambda as long as we have this lambda as the subscript, we have to understand that this is a property of a particular wavelength only. And that is not only for these quantities, but this is true generally for any quantity that will be discussed in terms of in the aspect of radiation. Right. Now, as I have said, radiation, like any other field, has been observational field by itself, observational field to begin with. So, initial observation, people used to talk about heat radiation and cold radiation, and so this is because if you are in front of, for example, inside a very cold room, you feel cold. So, that means you as if the walls of that room is radiating cold radiation. That used to be the thought. If you are in front of what you call a spile of ice, that means you can feel the cold coming from that ice. Okay. So, it is like cold objects will radiate cold radiation and warm object will radiate hot radiation. So, that used to be the concept. But around 1792-91, Prevost came up with his theory of exchange. So, what is said is all bodies with temperature above absolute cold, I am intentionally writing absolute cold because the term absolute zero was not defined at the year 1791. The term absolute zero was coined, I think, some 50 years after this, around 1840 by, I think, Lord Kelvin. But of course, there was a concept that there exists an absolute cold below which we cannot reach. Okay. The values were kind of predicted, but not exactly determined at that time. So, what he said was all bodies with temperature above absolute cold spontaneously emits radiation, and this is what it was very counterintuitive at that time, because not very counterintuitive at that time, but anyway he made this statement. So, two bodies inside a closed enclosure can attain thermal equilibrium by exchanging radiation at a rate determined by the temperature of the object. So, we have let us say, so the idea is we know that thermal equilibrium can be established by conduction and convection. He said that thermal equilibrium can also be established by means of radiation alone. If there is a closed chamber inside, let us say there are two objects which are placed side by side at of two objects of different temperature, and if the the chamber is evacuated, even then if we give it long enough time, these two objects will reach a thermal equilibrium just by exchange of radiation between them, right. A body radiates at thermal equilibrium as well. So, even after a body reaches thermal equilibrium, let us say inside an enclosure there are few objects, and if we wait long enough, according to Prevost's theory, they will reach thermal equilibrium. Now, Prevost did not stop there. He continued saying that even after reaching thermal equilibrium, there will be still radiation, but at the same time it will also absorb radiation from the other sources, other possible sources. Each object or each part of the wall is inside a closed container is a possible source of radiation. Not possible, it is a definite source of radiation. So, an object which is placed inside in a closed enclosure in thermal equilibrium will not only absorb radiation energy, not only emit radiation energy, but it will also absorb radiation energy at the same time. But being at thermal equilibrium, the energy that has been absorbed and energy that has been emitted will be equal and will be equal to each other. So, the net energy density or net energy of the body will not change with time. So, these are the three very famous statements he made, and actually this revolutionizes the field of radiation. Prior to that, I mean, people used to think of radiation in a very qualitative manner, but afterwards, after he came up with this statement, there has been numerous effort to quantify the concept of radiation. Okay. So, let us go into another very important concept which is called the black body. Now, what is a black body? An ideal black body is an object that absorbs all the incident energy on it irrespective of its wavelength. So, A lambda is equal to 1 and R lambda is equal to 0 is equal to T lambda for all lambda. So, that means a black body, an ideal black body will absorb everything, will reflect and transmit nothing for all wavelengths lambda. Okay. So, it is once again it is a idealized concept, but okay, I mean I am just giving you certain some more concept about black body which can be proved in a systematic way if we go step by step, but it will just take very long time to reach there. So, and certain concepts nowadays we are familiar with it even from our school physics. So, that is why I will just take I will just point out the main findings or main properties of black body during the course of this lecture, and as and when required we will prove certain properties of associated with the black body. So, an ideal black body also is a very good emitter. So, and that can be proved, that is a direct consequence of the Kirchhoff's law actually. So, it is an ideal emitter, and for each lambda it emits as much or more thermal energy as any other body in the same temperature. So, that means at a given temperature and given wavelength, a black body is the best emitter among all other possible objects. Similarly, okay, so this is one concept that probably will be proving that will come out as a natural consequence of Kirchhoff's law, which we will be covering this within this lecture itself. And secondly, it is a diffused emitter. Diffused emitter means a black body radiates in all directions. So, although we have just started saying that black body is a idealized, it is an object which absorbs everything, we have made two statements regarding the emission of the black body, because that is what is more interesting. We will see later on that black body radiation it's not only the field of it's not only the field of thermodynamics that benefited from blackbody radiation, but also the field of quantum mechanics has been immensely supported, or I should not call it probably, or I would say the blackbody radiation played a key part in the development of old quantum theory, right. So, we talk about blackbody as an ideal emitter, but mathematically speaking, a blackbody is defined by this simple relation. Now, it's just a natural consequence, thermodynamic consequence, that if something is a very good absorber, if it has a lambda is equal to 1, it will be a very good emitter as well, as we will see later. Now, how to realize a blackbody? A blackbody is an idealized concept, because no object can have 100% absorbance, or absorbance cannot be equal to 1 at any given wavelength. Now, there has been search for material which has very high absorption power. For example, very familiar material to us, which is carbon black. Now, what is carbon black? Carbon black is when we have a candle light burning. Sometimes we see our mother will complain that our gas stove is not working properly, and all the utensils becoming black underneath. So, this is nothing but, so that there must be some sort of a blockage in the passage of the gas, and due to some incomplete burning, lot of carbon deposits are being processed. So, generated, and those carbon deposits are nothing but carbon black. So, I think there are certain local names for it, I am not familiar to those, but we call it carbon black, and this is precisely what we get if we just take a piece of metal and place it inside on a candle flame. So, if we keep there for some time, a spoon, let us say, for some time, 1 minute or so, we will see there is a black coating. So, that black coating is nothing but carbon black. Now, carbon black has a absorptivity A lambda is equal to 96%, and that is across wavelength, and that eventually means the carbon black is also a good emitter. Okay, I will come to that later on. Platinum black, similar to carbon black, there can be processed platinum powder called platinum black, which is 98% it absorbs 98% of radiation of all wavelength that falls on it. Nano black, which was developed in 2009 by a group of Japanese scientists, it has 99%, nearly 99% absorbance, and there is a material called Venta black, which is actually I think patented product of a company from Surrey, UK, which has an absorption power of 99.996% as has been measured, right. So, you can actually search for this, and there are many interesting pictures and videos available from their official website, that this material actually looks really it can do wonders. Anyway, but these are modern. You see this nano black and Venta black, these are pretty modern in that way. So, in the early days, and I am talking about blackbody theories which has been developed over like 200 years back, or maybe at least 100 years back. So, in those days there are different devices that acted as ideal blackbody. One such device is Ferri's blackbody, which is basically a hollow sphere, okay, and there is a double walled sphere. Outer wall is there is a vacuum that is maintained inside this wall, and there is a small tiny opening. Just opposite to this opening, there is a sharp feature on the wall. And what is the role of this such sharp feature? Any incident radiation that comes in cannot be reflected back directly. So, instead it will fall on this angle, and it will randomly getting reflected inside this inside the cavity. Now, the inner side of the cavity is coated either with this carbon black, which is lamp black, carbon black is essentially the same thing, or platinum black, which will keep absorbing high percentage of light after on every reflection, and eventually after few 5, 6, 7, 8 reflections, almost everything 99.99% is absorbed. So, nothing is coming out of it, and the outer wall is nickel polished, so that the radiation loss is minimal, because if something is very good reflected, that means it is not absorbing anything, and we will see later on, if something is not absorbing, it will not also not emit that much. Okay. So, that is Kirchhoff's law, by the way. Now, this one acts as a black body, but please remember, only the opening of this it behaves like an ideal black body, this tiny opening. If a radiation falls on this surface, nothing happens, it will just be reflecting out. Okay. So, this tiny opening is your black body, this entire thing is the cavity inside, which helps to create this ideal black body, create this black body. Okay. And if the whole system is warmed now, it is put inside a furnace, this tiny hole itself, it will radiate energy, which can be called the black body radiation. Okay. So, there is another type of construction that is called the Wien's black body. It was first proposed by Wien and later built by Lumen and Princeton in 1898. So, this is a slightly different construction, where we have a cavity, a platinum cavity, and this is actually a metallic shield outside. There is a heater outside, through which we can actually control the amount of heat that is being generated. Now, this heat, it will be absorbed by this by the side walls, and a tiny amount can be taken out by adjusting this slit over here, this aperture here. So, if we open this aperture, a tiny amount might be coming out. So, this is also another type of instrument that has been used as a black body in a laboratory. The cavity radiation, and now for the rest of this discussion, we will be using black body and cavity radiation, these two words synonymously. Okay. So, this cavity radiation is isotropic, that means at any point the energy density of radiation in all directions are equal. Sorry, it should be L here, equal, and homogeneous, as the energy density is the same at any point within the cavity. So, what I mean to say is, if I choose any arbitrary point here or here or here, and the energy density at these points will be equal. Similarly, if I take any point, place a surface at that point at any possible direction, the total energy that will be incident on this surface will be equal. So, these are the two properties which are called isotropic and homogeneous. Okay, so we'll stop here for today's lecture. Next lecture we will be talking about something called the Kirchhoff's law and other properties of this black body radiation. Till then, thank you.